Let's think back to understand what we're doing here to that example of the race we talked about earlier, where, for the sake of specificity, we could say that that race was an Olympic trial. And at that trial, you're not just watching to see who wins, but you're watching because you're thinking of sponsoring some of the runners. And if you have the same budget for all of the runners, it doesn't really matter who you pick when. Obviously, you want the best runners, you want the most interesting runners, but, well, your considerations might not just come down to whoever happens to be the fastest. Some might have a particularly interesting story that you want to emphasize. So, if you're going to pick them, it might not actually matter to you the order in which you do so. And let's say that to keep it consistent, you care specifically about just 2 of them. Instead of getting all 3, let's say you only want 2, where if we care about the order, let's say order matters. Like we did in the last section, we would have 8 permute 2 options, which would end up being 8 factorial over 6 factorial. I'm skipping a half step there. Hopefully you're able to see where that became a 6 factorial. Obviously it's a little bit fast, but you'll get there. Which becomes 8 times 7 times 6 factorial over 6 factorial, or 8 times 7, or 56 options. But we're assuming here that order doesn't matter. And if we assume order doesn't matter, that is, we don't care about who we picked when, that would mean the 2 factorial arrangements of the runners, well, those don't really make that much of a difference to us. And the thing about this sort of counting is that because when we want more options, we always multiply. If we want fewer options, we always divide. It's the idea of how these factorials end up working out with permutations as well, though I didn't explicitly mention that. So, if we don't care about those 2 factorial options, what we could do is take times 56 equals 56g's. My grammar is going bad and my notation is going bad, but we would take that whole 56 and divide it by 2 factorial, where we would end up getting, in this case, because 2 factorial is 2 times 1 or 2, 28 options. And this points us towards our idea here, which is the combination number, which we write as n choose r. In this case, we are taking 8 choose 2. Or we can write it that way, or there's one other weird notation we use for this, where we make a big parenthesis and we put an 8 over a 2 there. That's the binomial coefficient idea. This is a very, very important construction that comes up in a lot of branches of mathematics. I've taught about a half dozen classes, a half dozen different topics, and I've had to mention something in this flavor at least once in all of them. So it is very important for math that we know how these things work. And what we're looking at here is selections of some number r things from a group of n where we don't care about the way that they're ordered. Where we have things like this. We have 2 that we're going to sponsor in particular. We don't care about that, so we knock out the 2 factorial choices. And if we want to think about how that works more broadly, we still have that n factorial total number of arrangements for all of our things. Then we remove the n minus r ones that we don't care about, just like before with permutations, and then we also remove the r factorial arrangements of the groups themselves that we don't care about. Where, when we're dealing with these things, that's the fundamental process we're following through on. We're taking some extra precautions here. We're taking out some cases for the fact that we don't care about the way in which they're organized. And what we should know is that because we don't care about the way in which things like this are organized, except in some very specific, very special cases, we have generally that n choose r is much smaller than n permute r. That is, outside of some special values for n and r, NCR is less than NP are. And you can very quickly see why that might work if you think about taking, say, groups of 3. That if you're picking 3 things and you don't care about organization, things like ABC, ACB, BCA, CAB, CBA, those are all exactly the same to you because those are 3 groups of A, B, and C. Whereas if you care about order, those are all unique selections. So if we care about order, we should get more options, and outside of those very special circumstances, we generally do. So, with the idea of what combinations do, what we're trying to do with them, and how we get our values, let's get some more practice here, like we did with permutations, for how these end up actually working out.